Very good morning, students. In this lecture, we will go through some numerical examples for the design of basal reinforcement that we had studied in the previous lecture, and then the planar wedge analysis for design of very steep embankments on competent soils, and some design examples. As you may recall from your other geotechnical engineering courses, these are the different types of failures that we can have with the slopes. Let us say that you have a slope of height h, and there are three possible modes of failure. One is the face failure. The face failure happens in the case of steep slopes, or if the embankment is formed with a relatively weak soil, and then the toe failure is the failure that happens when we have a strong foundation soil or a very shallow slope. Then base failure or deep seated failure happens when we have an extremely soft foundation soil and our embankment soil itself is relatively strong. And just to recall, in the previous lecture we have seen the design of soil slopes with the basal reinforcement layer, and the basal reinforcement, it is provided for several reasons. Especially in the case of extremely soft clays, we require a working platform so that we can even bring in our construction machinery and start mobilizing our equipment. And then of course, on top of that we may require some extra reinforcement to improve the factor of safety. And for a very simple case where our phi equal to 0, we can get the factor of safety for a given circle by just taking moments about this center of rotation, and if W is the weight of the soil within this wedge, and x bar is the lever arm, W times x bar is the destabilizing moment, and then the stabilizing moment is because of the cohesive force that is acting along this slip circle length, that is Cu times La, where La is the length of the slip circle multiplied by this r, radius r, and that is the factor of safety of the unreinforced slope. And if you have a basal reinforcement, we need to add extra stabilizing moment because of the basal reinforcement. And so we have seen two cases of basal reinforcement. One is a very stiff reinforcement that remains horizontal, and another is a flexible type reinforcement that bends, that has a kink at this slip surface, in which case the axial force in the reinforcement acts tangential to the slip surface. And now let us look at a numerical example. Let us consider a clay soil embankment, height of 8 meters, and the slope angle is 45 degrees, and let us say that both the slope and the foundation soil have the same soil properties of Cu of 25 kPa, and the friction angle is 0, and the unit weight is 20 kilonewtons per cubic meter. And for this situation, the toe circle is the most possible failure mode. And as we discussed in the previous lecture, we need to consider several of these slip circles to get the circle with the least factor of safety, and whatever equation that you have seen is only for one single slip circle, and we need to try out several of these to get our minimum factor of safety, and it is best done using some computer program. And in this case, this is the result from one computer program that you are going to get as part of this course. The height of this slope is 8 meters, and this slope angle is 45 degrees, and the factor of safety of this unreinforced slope is 0.92, and we need to increase this factor of safety to a higher value, and that is a trial and error process. And here we have the result from another slip circle analysis with basal reinforcement having a tensile strength of 200 kilonewtons per meter, and for this case the factor of safety is come up to 1.3, and we may need to choose a basal reinforcement that provides higher force in case if you want a factor of safety higher value, and the length of this reinforcement that we need to provide should be adequate, so that it has sufficient pull out resistance, and the pull out resistance is calculated based on the embedded length of reinforcement beyond the most critical slip circle, and these are all best done using some programs, because doing hand calculations is quite tedious, because typically we look at least 2 to 300 slip circles for coming out with this minimum factor of safety. And in this case, as I mentioned earlier, if we are not happy with this factor of safety, we need to increase the tensile strength of the reinforcement, and typically we do not provide one single layer as illustrated here. We may provide some 2 or 3 layers so that we can achieve our target factor of safety. And continuing our discussion, many times when we have road embankments and other things in the city areas, we may be faced with the requirement that we need to construct very steep slopes, and one example as we had seen earlier is like this. Let us say that we want to widen this road, and the only way to widen this is either to make this slope as a steep slope, and so that we get extra space, or procure more land and widen the construction area. And in the city urban areas, getting extra land for our construction is very difficult. So, in that case we go in for steeper slopes by providing horizontal layers of reinforcement. And how do we design this type of slopes? There are different design approaches. One is the slip circle analysis. We can just do the Fellenius or Bishop's slip circle analysis and find out the factor of safety. And here this equation is from the Fellenius analysis or the ordinary method of slices. Once again we take moments about the center of rotation, and for the convenience we divide this entire length of the slip circle into certain number of slices, typically at least minimum 6 to about 10, and if we consider the equilibrium of each slice, Wi is the weight of the soil that is acting down, and that causes some shear force Ti that is trying to destabilize this wedge, and that force is Ti time Wi times sin alpha I, that is just by resolving this force into parallel to this base and perpendicular to this base, and the perpendicular component Ni, the normal component is Wi times cosine alpha I, and let us say that the length of this base is Li, that is the inclined length, and we can calculate the factor of safety of the reinforced slope as the resisting moment divided by the upsetting moment, and the resisting moment is because of two components. One is because of the cohesion and the other is because of the friction angle, and the third one is because of the reinforcement that we have. And say if we are working with effective stresses C prime La, that is the length of this slip circle arc, multiplied by R, that is the lever arm for this cohesive force, and tan phi times Ni prime, and Ni prime is nothing but Wi cosine alpha minus U, that is the pore pressure, multiplied by base angle Li, and this pore pressure is we can estimate it if we have the phreatic surface, or in terms of the Bishop's pore pressure parameter, we can estimate U as some Ru times W, and this entire quantity that we have W times cosine alpha minus ui Li is similar to our effective stress, and this whole thing multiplied by R, that is the lever arm, and say we have certain number of reinforcement layers. We can take the summation of T times y, and that the resisting moment divided by the upsetting moment because of this component of the force Ti is Wi sin alpha I will give us the factor of safety of the reinforced slope. And this method is recommended in the Federal Highway Administration code, and even in the BS code they recommend, but it is only for preliminary analysis, and we have more number of other analysis that we can consider. One simple method is the planar wedge analysis of the steep slopes. We will understand the principle of the slope stability analysis with this, and we will go on for looking at more complicated surfaces. Let us say that we have a slope with an angle of beta, and then we want to analyze, and we have provided certain number of reinforcement layers, and the simplest one is if we assume that the failure angle is at an angle of phi, that is the angle of repose, that is the simplest one to consider. And let us say that there is a uniform surcharge of Q, and the failure is happening along the surface AC, and let us assume that our cohesive strength is C is 0, and the friction angle is phi, and the unit weight of the soil is gamma, and let us say that this is the AC is the assumed rupture plane at the angle of phi, and beta is the slope angle, and beta is much greater than phi, and RV is the sum of the weight of the soil within this wedge ADC and the loads acting on the surface DC, and N is the normal force on the AC, that is just simply RV times cosine phi. That is, if you can see this force triangle, RV is the vertical force, N is the normal component, and let us say that the sum of all the reinforcement forces is sigma Ti, that is the sum of all the reinforcement forces that we have, and we can do the equilibrium analysis of all the forces that are acting on the failure surface AC. As we have seen earlier, the normal force is RV times cosine phi, and the shear resistance is N times tan phi, because the friction here is between two soil surfaces, because here this slope AC is the rupture surface. On both sides we have the soil, and we can assume that the friction angle mobilized along that surface is only the phi, and the reinforcement force component upwards of the slope is just simply sigma of T times cosine phi, that is the component of the reinforcement force, and then the net shear resistance is N times tan phi plus sigma T cosine phi, and the shear force acting down the slope is RV times sin phi, that is that is the shear force that is acting down here. And if we consider the force equilibrium of all the forces acting along the sliding surface AC, our factor of safety is the shear resistance divided by the shear force, that is RV times cosine phi times tan phi plus sigma of Ti cosine phi, this whole thing divided by RV sin phi, and so cosine phi times tan phi is just simply sin phi. So, it is equal to RV sin phi plus sigma Ti cosine phi by RV sin phi, that is 1 plus sigma of Ti by RV tan phi, by bringing this cosine phi to the denominator. And RV is, as we discussed earlier, the weight of the soil within the triangle ADC plus the surcharge that is acting on the surface DC, and this length DC is H times cotangent phi minus cotangent beta, and our RV now is just simply 1/2 gamma h square times cotangent phi minus cotangent beta plus the surcharge force acting on the surface dc, that is q times h cotangent phi minus cotangent beta. And so, our factor of safety equation Fs is 1 plus sigma Ti by Rv tan phi, and by rearranging that equation we can get our sigma Ti in terms of the factor of safety and the other factors as Fs minus 1 Rv times tan phi, wherein our Fs is the desired factor of safety and this one is the factor of safety for soil to soil slope failure. And because we have assumed that the slope failure is along this this angle of repose, that factor of safety is 1, and this Fs is the desired factor of safety. Because of the provision of reinforcement layers, our factor of safety is going to be greater than 1, and so this sigma Ti is the sum total of the reinforcement capacities of all the layers provided in the soil to increase the factor of safety of the slope from 1 to Fs. And so, this quantity of reinforcement should be distributed uniformly over the height of the soil such that the reinforcement layers are not overstressed or subjected to pull out failure. Overstressed means the force that is transferred into each reinforcement layer should be lower than the tensile strength with some adequate margin of safety. And as we have seen earlier, in the case of reinforced soil retaining walls, the force transferred into each reinforcement layer at a depth of z is Ka times Sv of z multiplied by the vertical pressure gamma z plus q. In the case of retaining walls, we have considered Meyerhoff's pressure distribution, but in the case of slopes we just consider only the vertical stress without any effect of overturning. Here our Ka is the lateral earth pressure coefficient in the slope, but this is not equal to the Rankine's or the Coulomb's earth pressure coefficient. It is much lower because this Ka is operating in a shallow slope, and Sv of z is the vertical spacing at a depth of z, and the Q is the surcharge pressure acting on the slope surface, and gamma is the unit weight, and this Ka is the sin beta minus phi divided by sin beta to the power 1.5 plus sin phi square root of sin beta to the whole of square. And this quantity, if we substitute beta of 90 degrees, will be equal to our Ka for Rankine's theory, that is 1 minus sin phi by 1 plus sin phi, and for the slopes this is much lower, as we will see later on. And the pull out resistance is estimated based on the length of the reinforcement beyond the rupture plane, like this. So, in our case our rupture surface is at an angle of phi like this, and let us say our reinforcement length, total length is L. Out of that, L is the anchorage length, and this anchorage length Le is L minus this length. That length is h minus z times, where z is the height from the top, cotangent phi minus cotangent beta. So, this Le, if we have it, because our pull out resistance is mobilized on two surfaces, we have a 2 here multiplied by Le, that is the anchorage length times the vertical stress gamma z plus q times tan delta, that is the delta is the interface friction angle, or we can also write it as some mu times tan phi, because where mu is called as the interaction factor in the pull out mode of failure, and phi is the friction angle. Apart from checking for the reinforcement rupture and the pull out, we also need to look at some other modes of failure It is let us say that this entire length of soil slope behaves like a rigid body, and it is subjected to lateral earth pressure from behind. That is, one is because of the self weight of the soil that has triangular pressure distribution, and the other because of uniform surcharge that has a rectangular pressure distribution. And this rigid block of reinforced soil may slide away by sliding above the bottommost reinforcement layer, and in this case our shear resistance or the base resistance is developed only on one surface like this, and our total lateral force is 1/2 Ka gamma h square plus Ka times Q times h, where our Ka is the reduced earth pressure coefficient as we have seen earlier. And the most is actually this failure may happen at any depth, because wherever we have a reinforcement that may be the weakest plane, because the friction angle that is mobilized between the soil and the reinforcement is usually slightly less than phi, and we need to theoretically do the check at each and every reinforcement layer, but then the most critical one is at the bottom, because the lateral force is the maximum at the base, and if our reinforcement lengths are different at different depths, then we may have to check at all the depths, but usually we provide equal length of reinforcement in the slopes, because from the construction point of view that is more easy. And apart from this, the other earlier failures that we have considered, when our face is made up of wraparound facing, especially with geogrid or geotextiles, this length of wraparound we should check to make sure that there is good anchorage. If that wraparound length is not sufficient, it will just get pushed out, and then we may have a face failure, and the minimum factor of safety that is required for this mode of failure is 2, and for this what we do is we assume that this particular wraparound is resisting the force that is coming from this height of the soil, and then equate the pull out resistance of this reinforcement length to this lateral force, to make sure that we have adequate embedment length, and if it is not adequate, then we will have to increase the embedment length, and typically this embedment length is at least 1 meter. So, now let us consider a simple example. Let us design a reinforced slope which has 70 degrees angle, and the height of this slope is 9 meters, and the shear strength properties of the soil are C equal to 0, and the friction angle phi is 30 degrees, and the unit weight of the soil is 20 kilonewtons per cubic meter. Then the long term allowable design strength of the reinforcement is 25 kilonewtons per meter, and the pull out interaction factor is 0.8, and the sliding interaction factor is 0.7, and the uniform surcharge is 20 kPa, and then the thickness of the compaction layer is 250 millimeters. And as we have seen with the design of reinforced soil retaining walls, the vertical spacing between the reinforcement layers should be in multiples of the thickness of this compaction layer, and we are required to find the safe vertical spacing of the reinforcement layers and the length of reinforcement layers, and our required factor of safety is 1.5. So, now let us go back to our equations. Our Ka for this case is, if we substitute a beta of 70 degrees and a friction angle of 30 degrees into that equation, we get 0.212, and for a vertical soil retaining wall having a friction angle of phi, our Ka is 1/3, that is 0.33, whereas here this value is much lower, 0.212, and our RV, that is the vertical force acting in that triangular portion, that is the sum of the soil weight and then the surcharge load is 1/2 gamma h square plus q times height h, and cotangent 30, that is phi, minus cotangent beta, that is cotangent 70, that is 1354.4 kilonewtons per meter. And as you may recall, all our designs are done per unit length in the perpendicular direction to the plane of analysis. And if we substitute this, our sigma of t, that is the sum total of our reinforcement forces, comes out as 390 kilonewtons per meter, and our number of reinforcement layers is 390 by 25, that is approximately 16, and our 25 is the long term allowable design strength, and this long term allowable design strength should include the construction induced damage, biological induced damage, then chemical degradation, and then the creep reduction factor, as we have discussed in earlier lectures. And so, this the total reinforcement force required is 390, and the number of reinforcement layers is 16, and now we need to find the permissible vertical spacings at different depths. And for this, our permissible spacing is the T, that is the long term allowable design strength divided by the force transferred over the height of SV, that is the spacing, and that spacing if we equate T to that permissible spacing in terms of SV, our spacing comes out as T by Ka times sigma v, and this we need to do at all the depths, at some convenient depths. So, at a depth of 1 meter, the vertical pressure is 40. So, it is 25 by this quantity 0.212 times 40, and this comes out as 2.9 meters, but then our if we provide reinforcement at a very large spacing, we may have failure between two reinforcement layers, and because of that all the design codes, they recommend the maximum spacing that you can provide. Usually it is not more than 1 meter, because if we have very large spacings, each the soil height between the reinforcement layers may have failure, because as you recall, the action of the reinforcement is only in its own plane and the effect gets transferred to some height. So, here the last column is the provided spacing, that is 0.75 meters, and this 0.75 meters is in the multiples of the thickness of the compaction layer, that is 250 millimeters. So, if we do these calculations, at a depth of 2 meters it is 1.9, at a depth of 3 meters 1.47, and it's reducing. At the bottommost point 9 meters, it is 0.58 meters. So, theoretically we cannot provide 0.58, because our compaction layers are in a thickness of 250 mm. So, we need to provide at minimum 50 centimeter spacing, and as we go up, even at a depth of 7 meters, the spacing required is 500 mm, and at a depth of 6 meters, our permissible spacing increases to 840 mm. So, we can provide at 750 mm, and now we need to distribute these 16 layers over the height of soil by taking this as the guideline. The maximum spacing that we provide at any depth should not exceed these values. So, by trial and error we can provide the 16 layers. In this particular case, we can provide one reinforcement layer at the base, that is at 9 meters depth, and another at 250 mm, 8.75, 8.5, 8 and so on. And towards the top, we need one extra layer of reinforcement, because that is to take care of any surface compaction pressures and then the surface traffic that is moving on. And so, this we have provided as per the codal provisions, the topmost layer should be at a depth of one compaction layer. So, that is 250 mm in this case, and actually these provided spacings are slightly less than 500 mm, that is 250 mm, to accommodate 16 layers. And now we need to once we choose the vertical layout, now we need to choose the length of the reinforcement layers, and the length of reinforcement layers is very simple to calculate. If we understand that we need a certain minimum anchorage length, and the Federal Highway Administration guidelines say that minimum embedment length is 1 meter, and that means that the in terms of the criticality, the topmost reinforcement layer is the most critical, because that will have the least embedment length, assuming that all the reinforcement layers are of the same length. So, this I am calculating the length of the topmost layer, that is 1 meter is the length of reinforcement beyond the rupture surface, and the distance from the slope up to the rupture surface is 9 minus 0.25, that is h minus z times cotangent phi minus cotangent beta plus 1, that is 12.9, that is we can round it off to 13 meters. So, now we need to check whether this 13 meters length is adequate from the other considerations, and this is the schematic of the different reinforcement layers. We have totally 16 layers provided at different depths, as we have indicated here, and let us calculate the what is the minimum length required at some other depths. Let us say that at 5 meters depth, somewhere in between, in midway through, it is only 6.5 meters. So, so now let us aim for a lower length of 6.5 meters in the bottom portion, because in the bottom portion our length of embedment is going to be very, very high if we provide the full 13 meters, and we can try to economize by providing a shorter length of reinforcement in the bottom portion. So, now the provided reinforcement layer length is 6.5 meters up to a height of 5 meters and 13 meters beyond that height. Let us just have a very simple design, only two lengths, 6.5 meters in the bottom portion and 13 meters at the top of the slope. Let us now check for the base sliding, and the total lateral force is 1/2 Ka gamma h square, h is 9 meters, plus Ka times h times q, that is 210 kilonewtons per meter, and the shear resistance at the interface of the soil to reinforcement layer is average vertical pressure is 0.5 times 9 times 20, that is 90 kPa, and the shear resistance our shear interaction parameter is 0.7 times vertical pressure is 90 times tan phi, that is tan 30 times 6.5, that is 236 kilonewtons per meter, and the factor of safety against sliding is this 236 divided by 210, and this factor of safety this factor of safety is coming as 1.12, which is less than 2. So, it is not sufficient. So, we need to increase the length of the reinforcement. So, we need to increase the length of the bottom reinforcement layers to 13 meters. So, we can provide uniform length of 13 meters over the full height of the slope. And now we need to also check for the pull out and then the rupture. Let us check the topmost reinforcement layer, and the topmost reinforcement layer takes the force that is coming from the soil above this reinforcement layer, and the force over half the spacing to the next bottom layer. And so it is the SV is 0.25, that is the height of soil above that particular layer, plus 0.25 by 2, that is 0.375, and the vertical pressure at 0.25 meter depth is 0.25 times gamma plus q, that is 25 kPa, and the force transferred into this layer is Ka times q times SV 0.375, that is 1.99, and the pull out resistance, because at this height we have only 1 meter embedment length. So, it is 2 times 0.25 times 0.25 is the height of the soil times 20, because here I am ignoring the effect of surcharge, because as per the codal requirements we should ignore the effect of live load surcharge on the pull out resistance, because that is the worst case scenario. Actually that is also as per the case B of the BS 8006, and the pull out interaction parameter is 0.8, and this 2 is because we have the shear force developed on both the surfaces times tan 30 times 1 is the embedment length, that is 3.69 kilonewtons per meter. So, the factor of safety against pull out failure is greater than 1.5, it is coming as 1.8. So, it is safe. So, our the length of the reinforcement layer is 13 meters, that is sufficient as far as the pull out and the base sliding is concerned, and the vertical spacings are as designed earlier. And because our vertical spacing that is provided is much lower than the permissible spacings, we will not have any rupture failure. And so far we have discussed the stability of slopes under static loading, but in many cases we will have to design the slopes even for earthquake forces. And now let us include the additional forces that we have because of the seismic forces, and let us say that we have two extra forces Fh, that is the seismic force acting in the horizontal direction, and this horizontal force, because of the seismic action, could act into the soil or away from the soil, and in the worst case is the Fs acting away from the soil, and because if it is acting into the soil, it tends to stabilize the soil, and Fv is the seismic force acting in the vertical direction, and it could act either downward or upward, because it can act both ways, and if it acts downwards, it acts along with the weight of the soil. So, it increases the normal resistance, but then also increases the shear force, and if it acts upwards, it reduces the weight. So, it reduces not only the normal force, but also the shear force, and Fh can be written as some factor Kh times W, where W is the weight of the soil within the failure wedge, and Fv is the Kv times W, where Kh and Kv are the seismic factors, and there are so many empirical codes given to estimate the Kh and Kv values, and as we have discussed earlier, we need to use the IS 1893 for estimating these factors. So, now let us look at the pseudostatic analysis of this slope subjected to seismic action. Let us consider the same slope at an angle of beta, and the rupture surface is at an angle of phi, that is the most critical rupture surface, and we have earlier considered the normal force N T and then the shear force acting down. And now we need to consider two additional forces F h and F v, and F h is the horizontal seismic force, that is the most critical one if it is acting outwards, and F v can act either up or down, and the factor of safety of the unreinforced slope is like this, as we have seen earlier. And by considering the action of these additional forces, we need to consider we need to determine the factor of safety of the slope, the most critical case, and our the pseudostatic forces are the F h and F v, and the worst possible direction for the horizontal seismic force is the outward direction, whereas the vertical load, vertical force because of the seismic excitation is either to increase or decrease the effect of the weight. And if we resolve all the forces, our resisting force is C times L A and W minus F v times cosine phi, assuming that the vertical force is acting up, and minus F h sin phi, this whole thing times tan phi. So, you see that the effect of the horizontal seismic force is to reduce the resisting force, it is reducing the normal force that is acting, and this whole thing divided by the driving force, that is the W minus F v, that is the vertical force, plus F h cosine phi, and F h cosine phi is the shear force acting on the slope because of this horizontal component. So, this the horizontal seismic force reduces the factor of safety because it is reducing the resisting force while increasing the driving force, because it is reducing the numerator and increasing the denominator, whereas the effect of the vertical seismic force is the same, like it is decreasing the numerator and is also decreasing the denominator. Or if you assume that the vertical force is acting down, it becomes W plus F v in the numerator and W plus F v in the denominator. So, it is the effect of F v is very minimal, whereas the effect of F h is quite significant. And how do we select the K h and K v? Once again we can go back to our IS 1893, the code of practice for design of the seismic resistance of the buildings, and this we have already seen how to apply for the design of retaining walls. The same principles apply even for this case, and when we consider the seismic forces, our factors of safety can be reduced by reduced to 75% of the static values, as we discussed earlier. So, for example, if we need a factor of safety of 1.5 under static case, under seismic case it can be 1.125. Okay. So, that is the end of this lecture, and if you have any questions you can contact me at this email address. Thank you.